Welcome everyone. Thanks for watching this video. This is Chao Ye from UC Berkeley. Today, I'm going to talk about our latest research of hybrid resonant switch capacitor converters for data center power delivery and showcase how this technology can help improve the energy efficiency and power density of data centers. In this talk, after briefly introducing the background and research focus, I'm going to start with a high-level overview of the key idea and benefits of hybrid resonant switch capacitor converters. Then, I will present 3 high-performance hardware prototypes we designed and built to cover different power conversion needs of future data centers. Here, I'm showing a typical data center power delivery system, from high voltage AC grid down to very low voltage DC point of loads. To address the high ratio DC conversion from the 48 volt bus to the point of loads, a 2-stage approach is commonly used. In this work, we focus on the first stage, intermediate bus converter, from 48 volt down to a lower intermediate voltage ranging from 12 volt to 4 volt. Conventionally, power converters use magnetic components like inductors as the energy transfer element. The picture on the left side is a high-performance 48 to 12 volt buck converter using the latest gallium nitride switches. However, as can be seen from the picture, the inductor size dominates, indicating that passive components have become the bottleneck of the power converter. In comparison, capacitors can have energy density that is up to 1,000 times higher than inductors. The picture on the right side is an example switch cap converter. By cascading 2 of these together, near 98% efficiency can be achieved from 48 volt to 12 volt. However, it still suffers from a fundamental capacitor loss mechanism called capacitor charge sharing loss, which severely reduces the energy density advantage of capacitors. To eliminate the capacitor charge sharing loss and increase the efficiency and power density, the concept of hybrid switch cap converter is proposed. Here, an inductor is added to the capacitor charging path. It behaves as a current source and shows the voltage difference between capacitors. As can be seen from the plot at the bottom right, compared to the hard charging operation of pure switch cap converter, the soft charging operation enabled by the inductive element can result in much lower RMS current and power loss. This is a 48 to 12 volt cascaded resonant converter we presented at OCP last year. It consists of 2 basic 2-to-1 resonant switch cap converters with a total conversion ratio of 4 to 1. The inductor is selected to resonate with the flying capacitor, such that not only soft charging, but also soft switching can be achieved. It has a power density of 2,500 watts per cubic inch by considering the total box volume, and a very high peak system efficiency of 99.0%, with gate drive loss included. But we did not stop here. What are the next steps? The table here shows that the efficiency of the second stage buck converter is strongly dependent on its input voltage. It indicates that a lower intermediate bus voltage may provide a better overall 48 point of load efficiency. This requires high-performance bus converters with higher conversion ratio, such as 8-to-1 or even 12-to-1. However, there is one major challenge of switch cap converters at higher conversion ratio. As shown in the tables here, for all typical switch cap topologies with 2 operating phases, the component number increases proportionally with respect to the conversion ratio. This can result in increased circuit complexity, decreased performance, and other issues related to reliability and cost. To address this challenge and continue the promise of switch cap technologies, we developed 2 new resonant switch cap topologies that are specifically suitable for high conversion ratios. The first one is a 48 to 6 volt multi-resonant doubler. Compared to a voltage doubler with 2 operating phases, this proposed topology incorporates multiple operating phases within one switching cycle. It can achieve a conversion ratio of 8:1 with the least possible number of components. As shown in the plot, with one resonant inductor at the output, it can self-charge all flying capacitors at different frequencies while maintaining zero current switching. This hardware prototype has the same physical size as the 48 to 12 volt cascaded resonant converter, but with doubled conversion ratio. It has a power density of 1675 watts per cubic inch and a 98.0% peak efficiency, including gate drive loss. Second work is for 48 to 4 volt conversion. To achieve such a high conversion ratio, a two-stage approach is used. The first high voltage stage is an ultra-efficient 2-to-1 resonant switch cap converter. Then, with half of the input voltage, the series parallel topology is used for the second high current stage. By considering both the theoretical performance and the available passive and active components on the market, we find that this strategy can fully utilize all existing devices' potential. The operating waveforms are shown here. Both stages can achieve zero voltage switching, which can be very helpful for improving light load performance. Thanks for the efficient capacitor utilization of the series parallel topology, only very small inductance is needed for the resonant operation. As shown in the hardware photo, very low profile inductors are used to supply 60 amp output current. The converter can achieve 1154 watts per cubic inch power density or 308 amp per cubic inch current density. The peak efficiency is 97.0%, including gate drive loss. In summary, we demonstrate that hybrid resonant switch capacitor converters can be a very promising technology with both high efficiency and power density. Through proper topology selection and hardware implementation, it can be used as high-performance intermediate bus converters covering different bus voltages. At the end, I would like to acknowledge APAE for supporting this work. Thanks for watching. Please send me emails for any questions. My email address can be found on the poster.
Thank you for watching. I'm now available to take any questions. Feel free to ask anything under the Q&A tab. So there's one question regarding the voltage rating of the MOSFET in the circuits. So depending on the circuit we presented here, for the 48 to 12 and 48 to 6, it uses the voltage doubler topology. So the highest voltage rating of the MOSFET is half of the input voltage. Considering the 60 volt peak voltage, so we selected 40 volt MOSFET as the highest rating. There will be other lower voltage rating switches for those ones close to the output. So 25 volts MOSFETs are used. There's a question about the clock generation for the 48 to 6 volt multi-resonant doubler. For such converters, there are multiple different PWMs compared to usually a 2 two complementary signals. But still here, we use the TI C2000 microcontroller to generate the PWM signals. Another question is whether there are any commercial controllers available for now. For this kind of research purpose, we use either microcontroller or FPGA to generate the signals. However, if future commercialization is needed, we believe simple digital circuits can be generated because such converters operate in fixed ratio mode, meaning they're open loop, and we do not need to consider too much about feedback, and digital circuit, open loop digital circuit should be sufficient. The next question is, does the voltage stress become higher during the startup? The answer is yes. For this kind of test, we focus on the efficiency performance. So what we did is we ramp up the input voltage slowly. So the stress will not be a problem. If a hard startup is needed, we may need to rotate the top switch to the full voltage rating. There's another question about the tolerance of the flying capacitor and the inductor for the resonant frequency. A main benefit of all these topologies with the resonant inductor at output is we do not need to operate at exactly the resonant frequency. In fact, to further lower the conduction loss, our converters are actually operating at a frequency about 10% higher than the resonant. But regardless, we do not need perfect matching for such kind of operation. So there is a question about the switch number and the switch utilization regarding the 40 to 6 volt multi-resonant doubler. If we count the number of components, it is indeed has the least number of components with 10 switches and 3 capacitors in total. But in terms of switch utilization, this may need a further mathematical derivation. A trade-off for such lower number of components is it has less current conduction path. So under certain circumstances, it may have higher output impedance than the other topologies. So this is more like a design-oriented trade-off. Another question is whether the converters have zero current switching at turn-off. So the answer is if we operate at exactly the resonant frequency, we will have zero current switching at turn-off. But since we operate at frequency slightly higher than the resonance, so there will be slightly hard turn-off for certain switches without zero current switching. But from experimental results, we do not see significant effect on the efficiency. So there's another question regarding the comparison of these topologies compared to the switch tank topology. I would say that there are multiple all these topologies under the family of hybrid switch tank. The main difference of our topologies is we use a single inductor at output. The benefits includes higher tolerance to the component variations, and also the possible for regulation. And another thing is for the switch tank topology, it may be difficult to implement when the conversion ratio goes to higher, such as 6:1 or 8:1 or beyond. But we demonstrate with different topologies, we are able to maintain high efficiency and density at a higher conversion ratio. There's also a question regarding the possible integration. I would say that for such topologies, an implementation challenge is a high number of components, including switches and associated gate drive circuits. I would say there are a lot of opportunities of future works for integrating the switches together, along with the gate driver and the power circuit for the gate drive, such as DR MOS for the buck converters. With further integration, we are able to further improve the performance of such type of hybrid converters. And there's another question regarding the capacitor material. Here we use class 2 MLCC X5R. And depending on the available materials, such converters have very high tolerance to the variation. So various different types of materials can be used. There is another question regarding controller. Here we use the TI C2000 microcontroller for generating the PWM signal. Another question is, what are the major sources of loss for 48 to 6 volt and 48 to 4 volt? I would say that in these converters, as you can see from the efficiency curve, it peaks at a relatively low current and then start to drop. So for these converters, the conduction loss through the MOSFETs and also the PCB traces are the main source of loss. Okay, I think I have answered all of the questions here. And if you have further questions, feel free to send me emails. This concludes this session. Thank you everyone for watching. Have a good day.